Seen the concept of phase voltages and line voltages, Y connection and delta connection, and what is the relationship between the currents and what is positive sequence and negative sequence. I hope it is clear. So let's look at this one question. There are positive sequence balanced three-phase system in this figure. So what does this mean? Balanced three-phase system, all the loads are equal. And this is the source and this side is the load. Now the first is line voltages at the load side. The first part is to calculate line voltages, and because here we can see where is the line, this and this is the line, and the line voltage, it's a positive sequence ABC, and we start from picking from A to B. This is our line voltage, and this same voltage will be across the load here from B to A. This is the same voltage across the load. So if we are able to convert this phase voltage to our line voltage, this will be actually the line voltage that will be across the load. So sometimes students get confused, what does mean by across the load? And there are different topologies, different way of saying these things. E is usually used at the source side. Sometimes it is V. Sometimes it is E for EMF. But at the load side, they prefer using V. So EAB equals to actually VAB. Sorry. So don't get confused by these notations. Here small a, here capital A. The concept should be clear in your mind, and these letters can change. So basically this is our load, and this is the line B. Here is connected here and here. So this is the voltage between A and B, and this is actually VAB. So and this VAB is actually the voltage that is EAB, same voltage. So if we convert from EN to this voltage, it will be actually the voltage across the load. So how can we do it? We know the formula for a Y connection load. We know that the line voltages EAB is not equals to EAN. First of all, we know this thing. These two voltages are different. So the relationship that exists between them is under root 3 EAN. What is this voltage? And then we will add angle 30. Okay. So here we will have under root 3. What is EAN? It's 120 volts. We have 0, and the angle 30 will be added. So the value of EAB is 207.6 volts with angle plus 30. This I am solving part A. I am trying to calculate line voltages at the load side. Now once we know this is EAB, we have one voltage, so we can calculate EBC. That will be 207.6 volts. Do you remember? This is a positive sequence, and we have if we have VAB, then 120 degree shifted we have VBC, and then 120 degrees we have the other voltage. So we will get the angle will be minus 90 degrees, and the third one will be ECA, same amplitude, but the angle plus 120. We will add plus 120 in this, so we will get 150 degrees. So these are the voltages that I have got. Then in the part C, as you have just calculated them, so in the part C it says phasor diagram showing phase voltages and line voltages. So let's look at this, and it should be very clear to you now. So let's first draw the phase voltages. So here we have EAN. Look, EAN is this one, 120 volts with angle 0. So this will become EAN, or we can call it this is EAN, and then the next voltages is a positive sequence. This will be EBN, and this will be ECN. All will be having same amplitude, but the angles are different. Now we have also calculated our voltages EAB, we can see. So the EAB will be like this. It will be plus 30 degrees, and the rest of them you can easily draw. This angle will be, now this was the reference angle, so you can say, no, sorry. This will be minus 90 degrees, EBC, and the other one will be 150 degrees, like this. So, and this will be ECA. This is how we can easily calculate the phases for our voltages. Now let's look at the other part. I will be using the blue color. It says phase currents and line currents at the load side. So if you look at this, now this is a very good example of Y source and Y load. So this gives you a very unique opportunity. If we have this kind of circuit, if we know, look at this, and as we have discussed, this can also be converted into per phase equivalent circuit. So instead of worrying about all the three phases, what I can do is I can easily solve this circuit, because if you can see, this is the voltage EAN. Here the voltage between neutral is EAN, and this is actually the voltage that is also VAN. This is the same voltage that is coming here. So we can easily make a per phase equivalent circuit like this. This is the source, and this is the load, and this is the neutral point. So we know this is 120 volts angle 0. We have the load here. This is 4 ohms. We have an inductor. Impedance is 4 ohm. If we can solve this circuit, which current can we calculate? We can easily calculate the phase current, the current that is IAN. And you can either make this per phase equivalent circuit, or you can make this assumption that this is the voltage that will be across the load. So we can easily now calculate. So for the part B, what we can do, this was part C. For the part B, what we can do is, part B is asking phase currents and line currents. So the phase current is this current, and the line current is this current. We have to calculate. So I phase, that is equals to IAN, is actually equals to VAN divided by Z of phase, that is actually ZAN. So how to calculate ZAN? It is actually 3 plus J4, or you can perform the conversion, and it becomes 24 amperes. The value of this will be okay, yes, 5 ohms and angle will be 53.13. So this is actually what I have calculated the value of this, and so our VN will be 120 volts, angle 0, divided by 5 ohms, angle 53.13, and this will be 24. And so the current IAN will be equals to 24 amperes. IAN will be equals to 24 amperes with an angle of minus 53.13. This angle goes up and becomes negative. So from the negative current we can see this is lagging load. The current is lagging from the voltage. Voltage was 0 degree and this angle is minus 53.13. So now we have IAN. Can we calculate IBN? Yes. Now once you have one vector, you can easily calculate all the other vectors. You have to just, it is a positive sequence, so VBN will be 24 ampere minus 173.13 degrees, and ICN will be 24 amperes plus you will add and it will become 66.87 degrees. Now, so we have calculated the phase currents. Now what about the line currents? Now for the line currents, we know that in this case, as you can see, this is the phase current, the current that is going into the phase, and this is the line current. Do you see this line current dividing anywhere else? No, it is directly coming into the phase. So in this way, we know that for this case, I line equals to I phase. So IA equals to IAN. But this does not mean that IA is also equals to IBN. No. IB will be equals to IBN. So IB equals to IBN and IC equals to ICN. So the phase and the line currents. And here in the last part it says phasor diagram showing phase currents and line currents. Okay, so let's draw the phasor diagram which will show. So if this is our reference, so where will be our IAN? You see this is our IAN minus 53.13 degrees, and we have IAN, and where is here almost will be our IBN, and where will be our ICN? It is almost here, ICN. So where will be our line currents? The line currents are identical to the phase currents. So we can say this is also equals to IA. This is also equals to IB. This is also equals to IC. Do you see? This angle here is minus 173, and this angle from the references here is 66.87. So this is how I have solved a simple YY connected load. But there is one more thing briefly I would like to add here, that if you have, for example, this is the load. This is the load, and here are the lines coming. So I think A, if we say B, and here we have C. Now irrespective of what the source is. Irrespective it is star or delta, you don't need to get confused, because if you know the voltage, for example, if you know this voltage, if you know you are given VAB, you can calculate VAN. And once you know, you calculate, for example, VAB is, we have the expression VAB equals to under root 3 VAN plus 30. So if there is a value, for example, we have 100 volts, 0 degrees, we can easily calculate VAN. How? VAN, the phase voltage, we can calculate VAB 100 volts, angle 0, divided by under root 3, and here angle, this will go there and it will become minus. So this will become 100 divided by under root 3 angle minus 30. Now if we have VAN, we can easily calculate IAN. How? If we know the value of Z, we can calculate IAN to VAN divided by Z. And if we have the IAN, we have automatically calculated IA. Irrespective, here you have delta, you have star, you have moon, you have smile. But if you know these values, you can easily calculate this. Okay, I'll stop here and we'll do one more example.